Hello again everybody, thank you for joining me for the fourth video of chapter 2 for year 13 of Edexcel's A-level maths course on functions. So we've talked about domain and range. Today we're going to talk about how to find inverse functions and how they relate to the original functions themselves. So I'm going to try and illustrate this in itself with the warm-up to begin with. So we'll talk through the warm-up, which will hopefully reveal the main focus of today. So there's only two warm-up questions to have a go at. Here they are. Both revolve drawing the graph. Both revolve around drawing the graph of these functions and finding the inverses. So there's two functions, f of x and g of x. You need to find the inverses of each, plot the graphs of both the original and the inverse using the table of values to help, and then also state the line of symmetry that you notice that maps one to the other. So if one were a reflection onto the other, what would the line of symmetry be? So try these now, and when you're ready to see the solutions, press play. So assuming you've had a go, let's have a look together at warm-up question 1. So first off, f of x is 2x plus 1. We need to find the inverse, f minus 1 of x. So the best way of doing this would be to term, in my opinion, that f of x as y. So just let y equal 2x plus 1, and then we're going to make x the subject. So if I subtract 1 from both sides, I get y minus 1 equals 2x, then finally divide both sides by 2, I get that y minus 1 all over 2 equals x. So from this, I can therefore, by relabeling now x as f minus 1x and switching y for x, I've got the inverse. So f minus 1 of x is x minus 1 all over 2. So for part B, now what we need to do is to plot the graphs of y equals f of x and y equals f minus 1 of x. So if f of x is 2x plus 1, this essentially is the nth term. This is 2n plus 1. You can use a table of values to calculate this, but I'm just going to show you what the table of values would be. It would be as follows. So in fact, I've done the inverse in a red colour on this graph. So I'll just change this to a red so it's colour consistent. And so the original function, y equals 2x plus 1, f of x is 2x plus 1, is actually this graph here. So if I show you the graph of y equals 2x plus 1, it looks a bit like this. So that's the original graph of f of x. So there's f of x. And then if I show you the table of values for f minus 1 of x, the inverse function has this table of values. And this graph, when plotted, would look like this. So that's f minus 1 of x in red. Now, for part C, stating the line of symmetry that maps f of x to f minus 1 of x, hopefully you can see between these lines, exactly halfway between, if you bisected this angle, it would be on the line y equals x. So the line of symmetry is this dotted line, y equals x. So the line of symmetry, again, one to the other, is y minus x. So that's question 1, how the inverse relates to the original and the line of symmetry. But is it the same for question 2? So warm-up question 2, g of x is x squared, where x is any real number, so long as x is at least 0. So first of all, find g minus 1 of x. It says here to restrict the range of g minus 1 of x, such that g minus 1 of x is at least 0. So very simply, what we're going to do here is we're just going to term g of x as y. So if I just say y is x squared, then square root both sides, I can say that therefore y is going to be the square root of y rather, plus or minus equals x. However, looking at this, we want to restrict the range so that the inverse is at least 0. So what we're going to do here, we're going to eliminate the option that we can have it as a negative value. So therefore, putting these two bits together and swapping around the letters, x I'm going to say is g minus 1 of x. So therefore I have that g minus 1 of x is simply going to be the positive root of x. So in terms of plotting these, if g of x is x squared, we would have these table of values. I've done g of x now in red, so I'll do the inverse in blue. So if I just show you the original, the graph of x squared in red, then we'd have something looking like this, of course. And then the inverse, the square root of x, table of values would look like this. These values have been rounded to one decimal place, because obviously you're going to get decimal answers for root 3, root 5, and so on. And so this table of values would give rise to a graph looking like this. And again, if you look here about the line of symmetry that takes one to the other, you should ideally see again that once again it's in the line y equals x. So the same as before, the line of symmetry that takes one curve to the other, one function to the other, is the line y equals x. So bear that in mind from warm-up questions 1 and 2, what we found, and let's just take these ideas further. So the main ideas, let's go slightly deeper. So inverse functions. So the inverse of a function f is a function that reverses essentially the operations performed by the function f. An inverse function will take the elements in the range and map them back to the elements in the domain. And so essentially the function f takes elements from its domain, maps them to a range, and then the inverse will take bits that have just gone to that range and take them back to the original domain. So it recycles them back to its original state. So as we've seen in these warm-up examples, both pairs of inverse functions have the same line of symmetry, y equals x. So I've only shown you two different questions in the warm-ups, but this is actually universally true for any pair of inverse functions. They'll always have this line of symmetry between them, the line y equals x. So as I say, that's true for every single function and its inverse. So the original function maps x to y, then the inverse, as I've said again, maps each particular y back to x. It's just saying the same in different language, essentially. Thus, the original range of original is the domain of the inverse, and also the domain of original is the range of the inverse, and vice versa. So in really simple terms, we can think of the axes and the coordinates as swapping places when we make the inverse, and we can actually see this with some of the coordinates from the worked examples. So if I first of all pick on this one here from question 1 of the warm-up, if I just pick a few coordinates here from the blue and the red, for example, this one here is 2, 5, that can be thought of as being mapped to 5 and 2, and so x and y looks like they swap places, and essentially that is what happens. Taking another pair of coordinates, 1 and 3, maps to the coordinate pair 3 and 1. The graph of x squared and square root of x, again, each one would map to its corresponding pair. So just to take a couple here, 2 and 4 goes to 4 and 2, and 3 and 9 has a corresponding coordinate pair at 9 and 3 on the inverse function. Again, just swapping round the values. Now there is yet another way of thinking about the inverse, which I often toy with explaining to students from year on year, changing my mind sometimes from one year to the next. You can think of it essentially as a rotation and a swapping of the axes on the coordinate grid itself. So let me just explain. If I take the graph of the original function for question 1, which is a graph of y equals 2x plus 1, then we've got this blue line here, linear, obviously, as we can see. However, if we just literally swap, as I say here, it's like the coordinate axes swapping places. So if I call the y-axis x, and if I call the x-axis y, just swap the letters round, like so, then that essentially is the inverse. But of course, we're used to x going from left to right, but at the minute x is going up and down, which just seems a bit weird. So what we need to do now is to rotate this 90 degrees clockwise, like so. If we do that, x will run from left to right, and y will be going vertically, but actually this y arrow, when we rotate it 90 degrees, will be going down. Now in some alternate universe, this might be absolutely fine, but our convention is to have the y-axis pointing up. In the same way, this is just as weird as if we had a world map looking like this. There's no reason to say why this is logically wrong. It's just counter to our convention. It just looks pure weird because we're used to the map being orientated in the opposite direction. So although this is right in its own peculiar looking way, it's opposite to our convention, so this needs to be flipped in order for it to make sense to us. So in the same way, all we need to do here is to flip the y-axis so it faces the right way up. So if I just do a flip on the y-axis, then it transforms to this, which is the inverse of this one. So I've taken y equals 2x plus 1 and created its inverse here by thinking of it as a rotation of the axes and the axes names swapping places. I can do the same as well for y equals the square of x. So again, if I swap the y and x labels, this is going to be x now, and that's going to be y. Rotate 90 degrees clockwise, I then get this. X is now facing the right way, going from left to right, but y is going down. So flip mirror in the y-axis to get it facing the right way. And once again, this is a different way I can conceptualize creating the inverse from the original. Slightly unorthodox, but it is one way it can be pictured, and it is absolutely valid. Let's now try some questions together to build our understanding up. But before we do that, just let's generalize. So in general, a few key points. If functions f of x and f minus 1 of x are inverses of each other, then f of f minus 1 of x will always equal the inverse of f of x, which will be the original element itself. So in other words, you can think of the inverse as undoing the function, and the function as undoing the inverse, giving back the element as it was. One undoes the other. Also, the graphs y equals f of x and the inverse are reflections of each other in the line y equals x. That's always the case, as we've seen in these couple of warm-up examples. The domain of f of x is the range of f minus 1 of x, and the range of f of x is the domain of f minus 1 of x. And that's always true with inverse functions. The range and domain essentially switch. The function f of x must be a one-to-one function. This is a key point, a common one marker in examinations. A function can only have an inverse if it's a one-to-one function. If it's not a one-to-one function, it cannot have an inverse. So let's take that forward and practice. So let's have a look at a worked example. Some properties of inverse functions. So first of all, we have a function f of x defined by f of x being x squared minus 3x minus 4, where x is any real number, so long as x is at least 3 over 2. So first of all, what we need to do is to find f minus 1 of x, essentially find the inverse. Now, I've picked one here where it's got multiple instances of x, because this can be a common point of confusion. If we've got a quadratic like this, it needs to be where we have only one instance of x rather than two. Essentially what we need to do here is to complete the square. So I'm going to call f of x y. So I'm going to call it y equals x squared minus 3x minus 4, and I'm going to complete the square on that. So I'm going to say y equals x minus 3 over 2 squared. Then I need to subtract away 3 over 2 all squared. 3 over 2 all squared is obviously 9 over 4. But of course I'm still taking away that 4. So all I've done at this stage is I've taken the x squared minus 3x and completed the square on that bit of it like so. So that now simplifies to y equals x minus 3 over 2 squared. And minus 9 quarters minus 4 is the same as minus 25 over 4. Now that it's in this form, we can now reverse it to find the inverse. So if I now add this 25 quarters to both sides, and I get that y plus 25 quarters equals x minus 3 over 2 all squared. Now square root both sides, so y plus 25 over 4 all square rooted. That's going to equal x minus 3 over 2. Now you're probably screaming out, well I hope you're screaming out behind screens thinking plus or minus for square root, and you're right to think so. So it's a case of ambiguity here, but let's just think about if we can actually undo some of that ambiguity before by thinking about the function, how it's been defined. So we might just skip ahead to another part of this question here. So f of x, if I just highlight in blue what f of x actually is, it's this thing here. And I've got f of x in completed square form like this. So x needs to be at least 3 over 2. So we're going to start it when it's at its minimum. So when x is 3 over 2 and minus 6.25, that's what y would be, that's a turning point. It's going to start here. And because x is 3 over 2 or greater, we're just going to see the curving up right-hand side of a parabola, something a little bit like this. So that's f of x. And that point here is the point 3 over 2, minus 25 over 4. Now what we've learned is that actually the inverse will always be a reflection of the original in the line y equals x. So if I just think about this now, we can actually think about if you want the plus or minus version of this y plus 25 over 4. Now, if I reflect this in the line y equals x, quite clearly, I'm hoping quite clearly anyway, it's going to be something like this. So this point here is going to mirror, if I can just do this for a second, that's going to mirror to be over here. And then if I reflect that, it's going to be something like this. Not best drawn, but hopefully that gives an idea. So the red is going to be f minus 1 of x. So I'm hoping by use of a sketch we can see that actually we do just want the positive version of that square root. So then if I add 3 over 2 to both sides, I can say that therefore x is going to be the square root of y plus 25 over 4, filling out space here, small writing, plus 3 over 2. But of course, for part A of the question, I don't mean part A as in party down. For part A of this question, I want it to be f minus 1 of x, so I need to switch x for f minus 1 of x. So the answer to part A is therefore that f minus 1 of x, with bringing this here, f minus 1 of x is the square root of x plus 25 over 4 plus 3 over 2. Now, part B, essentially what we did in part B. It says label the x and y intercepts of each graph though, and also to sketch on the line of symmetry between the graphs. So we sketched on the line of symmetry, that's the line y equals x, so I'll add this on as well. That's the line y equals x, like so. And then to think about the x and y intercepts of a graph, this is going to be a slight bit of working, but actually nothing overly arduous. So if we have a look at the graph of f of x, there's only actually one intercept on this graph, which is here. And we can find the roots of f of x actually by factorising. So f of x, if I just doodle here, I can factorise this. Two numbers that multiply to minus 4 add to negative 3. That's going to be positive 1 and negative 4. So I can say f of x is factorised as x plus 1, x minus 4. So therefore, we know the roots would be when x is minus 1 and when x is positive 4. Just by inspection of this graph, though, we can see here that this isn't where x is minus 1. This is where x is a positive value, so we can reject that. This is where x equals 4. So that coordinate is 4, 0. And then if we just remember that the inverse essentially just swaps the coordinates over, without any further working, we can deduce this one here, the y-intercept of f minus 1 of x isn't 4, 0, but 0, 4. We also labelled y equals x, and so we've completed our sketch. State the domain and range of f of x. So for f of x, the domain, well, it's been given to us here, hasn't it? The domain of f of x is x can be any real number so long as x is equal to or greater than 3 over 2. We've not been given its range. We needed to work that bit out ourselves. So for range for f of x, essentially we found the minimum point, and f of x can only be equal to or greater than its minimum. So the range of f of x is that f of x is at least the value of its y value at its turning point, which is minus 25 over 4. So f of x is at least minus 25 over 4. Then for d, we can use our answer to c to help us. So for f minus 1 of x, for the inverse, the domain of the inverse is the range of the original. So the domain of the inverse is going to be that x is at least minus 25 over 4. And that shouldn't be any surprise, really, if we just go back to our graph for a second. This is where the graph of f of x starts. Its minimum point is 3 over 2 minus 25 over 4. Then just remembering that the inverse swaps these coordinates over, this f minus 1 of x graph here starts at this coordinate. This x value will be minus 25 over 4. In other words, the smallest value of x we have is minus 25 over 4. That's where the domain starts. And that's got a height of 3 over 2. So just by consideration of this graph again, we've now also deduced our range. So the lowest it starts at is at 3 over 2. It's only going to go higher. So the range of f minus 1 of x is that the inverse has to be at least 3 over 2. I could have said x being any real number as well for these, but it's probably okay to not do. E, again using the sketch, use the sketch to deduce the solutions to the equation f of x equals f minus 1 of x. So where does the blue curve hit the red curve? Now essentially we can see here it's going to meet and both hit the line y equals x. So rather than setting it so that x squared minus 3x minus 4 equals the square root of x plus 25 over 4 plus 3 over 2, it's actually easier to say these are going to be solved. The solution is where x squared minus 3x minus 4, or I could have said where this thing here, but because this has a square root, I think this is a more complicated equation to use. So I'm just going to say, where is this blue line equal to the line y equals x? In other words, where does the line y equals that equal the line y equals x? That's the key insight. Now we can solve this equation using calculator technology if we wish. So if I just subtract an x from both sides now, and I'm solving for x squared minus 4x minus 4 equals 0. Now at this point, you can do it manually or use a calculator technology, depending on how the question is worded. But just show how to do this on a class whiz. If I go to menu, option A, different models now have different versions of this, by the way, different steps, but the newer class whiz does have this function too. So go polynomial degree 2, because a degree 2 polynomial is a quadratic. Now what we're solving is x squared minus 4x minus 4 equals 0. So 1 for x squared, type minus 4, and minus 4 again, press equals, and press equals again. So in exact form, we have x is either 2 plus 2 root 2, or the second solution is x equals 2 minus 2 root 2. But looking here, that gives us minus 0.828. So if we just have a look at using our sketch, x is clearly going to be a positive value at this solution. It's not going to have a solution where x is negative. They would never cross where x is negative. The blue would never meet the dotted line. So actually our only solution in exact form is x equals 2 plus 2 root 2. Now it's over to you to try this task yourselves. So there's 4 different pairs of functions and inverses to work on. So for each one, what you need to do is to use your algebraic manipulation skills to find the inverse functions of each one which is given. The second thing, deduce the domains and ranges for the original function and its inverse. And then finally, label f and f minus 1 on each diagram, so which one's which. So first of all, this one we've got f of x is given as 3x plus 1. So what we need to do first of all, well in fact we can do these in any order we want to be fair. So f of x is 3x plus 1. It's going to be this line or this one here. Now this one's very straightforward, I think. This is y equals mx plus c. It's going to cross the y-axis at positive 1. It's got to be this one here. So for this one, the domain and the range is simply that x is allowed to be any real number. And the range is also that f of x can be any real number too. In fact, what I'll do, I'll put this in blue so it matches according to colours. So now what we need to do is to find the inverse. So if I just call f of x y for a second, let y equals 3x plus 1. I'm going to make x the subject. That's how I'm going to find the inverse function. So if I subtract 1 from both sides, I then get y minus 1 equals 3x. Then I can divide both sides by 3. So y minus 1 all over 3 equals x. And so therefore I can just switch x for f minus 1 of x. So f minus 1 of x, and switch y for x. So instead of y minus 1 over 3, that becomes x minus 1 over 3. So f minus 1 of x is x minus 1 all over 3, which I'm going to do in red. And so the inverse is that one there. As you can see, again, it's going to have the line of symmetry y equals x between them. Not that we're asked to draw this on, but just for the sake of it, I'm going to draw it on anyway, just so you can see clearly that it's always y equals x is the equation of the line of symmetry for all functions and their inverses. So for f minus 1 of x, the domain is the range of the original. So because both domain and the range are unrestricted, it's the same for the inverse as well. So the domain of the inverse is x can be any real number as well. And the range of the inverse is that the inverse 2 is allowed to take on any real number value. The second bit, this is a reciprocal one now. So f of x equals 1 over x minus 1. And so this one here, again, I'm going to just label this one in blue. By inspection of this function, what's it not allowed to be is what I'd consider for the easiest process to find the range, sorry, the domain. What values or value of x is not allowed here? Well, we can have x as anything. So actually the domain as x is allowed to be anything, almost anything. But, of course, if x was 0, we can't divide by 0. So we need to restrict the domain to say that x is any real number, but x cannot be equal to 0. The range of a function, in terms of what this can be, of course, x isn't allowed to be 0. So actually, this function here, f of x, is this blue line here, because it's not ever where it's at 0. So this is the original in blue. I'm just going to trace over it. Not very well, sadly, I'm not very good at doing this. And the range, again, the range can be more or less anything apart from the limiting case if x were approaching 0, which of course it's never allowed to be. In the limiting case, if 1 over x approaches 0 as x gets huge, f of x would approach minus 1. But because, of course, 1 over x can never quite be equal to 0, f of x can never quite get to being minus 1. So that links to the asymptote, in fact, on this one, which I'm going to draw on now. So if you have a look here, this line, that's where y can never quite touch. That's the line y equals minus 1. So what this says is the range is actually that f of x can be anything apart from minus 1, because that's an asymptote. So what we can do now is consider the inverse function. So I'm going to call f of x y, let y equal, in fact I'll do a different colour, I'll just use black. So call y 1 over x minus 1. Let's make x a subject. So adding 1 to both sides gives us y plus 1 equals 1 over x. Now y plus 1, I'm going to write this as a fraction all over 1. What I can then do is I can cross multiply. So in other words, x multiplied by y plus 1 equals 1 times 1, which is 1. So x times y plus 1 equals 1. Then dividing by the bracket y plus 1 gives me that x equals 1 over y plus 1. Therefore, the inverse function, f minus 1 of x replaces x, and then y is replaced by x itself. So the inverse function is 1 over x plus 1. So if I just trace over the inverse in red, the inverse is this curve here, which is slightly higher than this one here. And yet again, if you were to draw on the line of symmetry, again you'd see that it goes through y equals x. That line there is the line of symmetry mapping one to the other. So the next bit, the domain and range of the inverse. So the domain of the inverse is the same as the range of the original function. So the range of the original function is that it could be any real value apart from negative 1. In the same way here, you can see that if x were negative 1, that would just make the whole thing explode. So here the domain is x, any real value, but x cannot be equal to minus 1. And the range of the inverse is the same as the domain of the original function. So the range is going to be that it can be any real number apart from 0, which you can see here. This fraction can never be 0. It can be very, very tiny, but never exactly 0. So the range is f minus 1 of x, the inverse, can be any real value, but f minus 1 of x is never going to be equal to 0. Now let's have a look at the other couple of ones for you to try. So this one here, we've got an ln function. So f of x equals 2 ln x minus 1. So again, doing this in any order you prefer. The domain, what we need to know is that if we take the natural log, that actually x can be anything as long as it's greater than 0. So the domain of this one is that x can be any real value, but x must be positive. We can't take a log of a 0 or negative value. The range of this function as well, as long as x is non-negative, as long as x is positive, essentially the range is that f of x can take any real value. So f of x ranges from negative to positive infinity. So f of x here is this curve. So this is the blue one underneath. What I'm now going to do is rearrange to find the inverse function. So if I call f of x y again, so y equals 2 ln x minus 1. If I add 1 to both sides, I get y plus 1 equals 2 ln x. Using the laws of logs, I can put this 2 as a power of x. So I can rewrite this 2 ln x as ln x squared. So y plus 1 equals ln x squared. If I now exponentiate both sides, raise both to e, so e to the y plus 1 will equal e to the power of ln x squared. E and ln essentially cancel each other if you like, so that'll just give me x squared on the right hand side. So e to the y plus 1 equals x squared. Square root both sides, I get e to the y plus 1 all square rooted over here. Now you're probably begging, shouting, saying, well, that should be plus or minus here, and of course it should, but of course if we just consider the inverse and the graphical properties of that, we'll know that it's got to be a reflection in the line y equals x. Therefore, we can see here that it's got to be positive only. So f minus 1 of x is the positive root of e to the power of x plus 1. So, for this one, the domain is going to be the same as the range of the original function. So as you can see here, there's no restriction on the domain. X can be as small as you like, and as we get bigger and bigger, as big as we like. So the domain is simply that x can be whatever we want it to be. The range of the inverse is going to be the same as the domain of the original function. So the range, of course, we can see here that this red line is always going to be positive. So the range, f minus 1 of x, can be any real value, but f minus 1 of x must be greater than 0. And the final one to have a look at is where f of x equals the root of x minus 4. This one is this blue curve here. That's where x is 4. The inverse will be this point here, 4, 0, becomes 0, 4. So I know now this is going to definitely be the inverse function. And once again, we can see that the line of symmetry, as ever, is in the line y equals x. Like so. So, filling in these boxes in any order, the domain of f of x, clearly x can be any real number, but it's only defined when x is 4 or greater. So x has to be no smaller than 4. The range of this is, of course, that it has to be non-negative. So it is defined at 0, because you can do the square root of 0, but it can't be defined for anything less than that, because we're only taking the positive square root. So the range of f of x is that f of x is at least 0. And I could have said f of x is a real number as well, I suppose. Now let's work out what the inverse function is, the red. So if I call f of x y again, so y is root x minus 4. Let's make x a subject. First step, square both sides. So y squared equals x minus 4. Now I can add 4 to both sides. So y squared plus 4 equals x. So therefore the inverse function f minus 1 of x is, instead of y squared plus 4, switch y for x, the inverse is x squared plus 4, which is this one here. The domain of that is the same as the range of the original function. So the domain is that x has to be at least 0, as you can see here. X isn't ever negative, so x is at least 0 for that. And the range is the same as the domain of the original. So the range is going to be that the inverse can be any real value, apart from we need to have that the inverse function f minus 1 of x is at least 4, because of course it's no lower than 4. And then we're done. Well, I'm done. Now it's over to you to do some of the work for yourselves, of course. Get some decent, effective, valuable practice in. The questions I'd like you to try, or I'd suggest you try, are the following. Turn to page 38 and 39, exercise 2D in your blue Year 2 book. Questions 5 through to question 12. Try questions 1, 2, 3 and 4 if you can, of course. You need a bit more extra practice. But questions 5 through to 12 are the key ones, in my humble opinion. So try these, let me know if you're getting stuck, and always come to me for help if you are unsure, or put a comment even on the video. Either way, reach out and I'll do my best to try and clarify any issues. But as ever, I'll finish with the following. Thank you sincerely for watching the video. Please give it a thumbs up and a like, and stay tuned for the next instalment. So until next time, thank you very much, and I'll see you hopefully soon.